Welcome to today's paper reading. Today's paper is titled Self-Discover, Large Language Model Self-Compose Reasoning Structures. This paper was published on the AR14 preprint by Zhou and colleagues from the University of Southern California and Google DeepMind. The Self-Discover framework is designed to enhance the reasoning capabilities of large language models, LLMs, by addressing complex problems that are challenging for traditional prompting methods. At its core, the framework involves a self-discovery process where LLMs select and compose multiple atomic reasoning modules into explicit structures that guide the decoding process. This approach has shown significant improvements in performance, with up to a 32% increase compared to the chain of thought (COT) method on benchmarks like BigBench-Hard, grounded agent reasoning, and math. Additionally, Self-Discover outperforms more computationally intensive methods like COT self-consistency by over 20%, while requiring 10 to 40 times fewer inference computations. The self-discovered reasoning structures are also shown to be universally applicable across different model families, from PaLM 2L to GPT-4 and Llama 2, and exhibit commonalities with human reasoning patterns. The introduction of this paper discusses the impressive advancements in large language models, LLMs, in generating coherent texts and following instructions. Various prompting methods have been proposed to enhance LLMs' reasoning and problem-solving capabilities, inspired by cognitive theories of human reasoning. The paper introduces Self-Discover, an approach that aims to self-discover the underlying reasoning structure unique to each task, inspired by how humans internally devise a reasoning program for problem-solving. This approach is computationally efficient and results in a reasoning structure that is intrinsic to the task and more interpretable than optimized prompts. The paper highlights the benefits of Self-Discover, including its grounding in atomic reasoning modules, computational efficiency, and interpretability of the discovered reasoning structure. Figure 1 illustrates the performance of Self-Discover in guiding large language models, LLMs, to self-discover and compose atomic reasoning modules into a coherent reasoning structure. This structure is designed to solve challenging tasks across various benchmarks, including BigBench-Hard, BBH, agent reasoning, T4D, and math. The results show that Self-Discover significantly outperforms both direct answering and chain of thought (COT) methods in a zero-shot setting using PaLM 2L. Specifically, Self-Discover achieves superior results on 23 out of 25 tasks compared to direct answering and on 21 out of 25 tasks compared to COT. These findings highlight the effectiveness of Self-Discover in enhancing LLM reasoning capabilities across diverse and complex tasks. In Stage 1 of Self-Discover, the process involves 3 key actions: select, where relevant reasoning modules are chosen based on task examples; adapt, where these modules are rephrased to be more specific to the task; and implement, where the adapted modules are turned into a structured plan for solving the task. Stage 2 then uses this implemented reasoning structure DI to solve every instance of the task by prompting models to follow the structure and generate answers. The process is guided by metaprompts that help in selecting, adapting, and implementing the reasoning structures. Figure 2 illustrates the process of using Self-Discover for problem solving. It starts with a generative language model, a specific task, and a set of seed reasoning module descriptions. The key step is guiding the language models to generate a reasoning structure in a key-value format tailored to the task. This structure is then used to solve each instance of the task by filling in the values based on the keys during the decoding process. This approach ensures that the models follow a structured and logical path to arrive at the final answer. The experiment setup involves several key components. Firstly, the tasks include the BigBench-Hard (BBH), which contains 23 challenging tasks, the Thinking for Doing (T4D) task, and a subsample of 200 examples from the math test set. These tasks are designed to test a variety of reasoning abilities. Secondly, the models used in the experiments are state-of-the-art large language models such as GPT-4, GPT 3.5 Turbo, PaLM 2L, and Llama 2-70B. These models are chosen for their advanced reasoning capabilities. Lastly, the baselines for comparison include direct prompting, chain of thought, COT, and plan and solve, PS, methods. These baselines are used to evaluate the effectiveness of the proposed self-discover method. Figure 3 illustrates the three key actions of self-discover: select, adapt, and implement. These actions guide large language models, LLMs, to compose a coherent reasoning structure by first selecting relevant reasoning modules, adapting these modules to be more specific to the task at hand, and finally implementing a structured reasoning plan in JSON format. This process ensures that the reasoning structure is tailored to effectively solve the given task. Table 1 demonstrates the significant improvement in large language model, LLM, reasoning capabilities across a diverse set of 25 complex tasks, including BBH, T4D, and math. The table compares the performance of LLMs using self-discover with other zero-shot prompting methods such as chain of thought, COT, and plan and solve, PS, prompting. Key metrics include accuracy rates for each method across the different tasks, highlighting the enhanced performance of LLMs when utilizing self-discover. The results demonstrate that self-discover significantly enhances the reasoning capabilities of large language models, LLMs. It performs particularly well on tasks requiring world knowledge, such as understanding sports, recommending movies, and recognizing ruin names. On the BBH tasks, self-discover achieves notable improvements, with significant gains observed on the T4D task and moderate gains on math tasks. Efficiency-wise, self-discover requires fewer inference calls compared to other methods, making it both accurate and cost-effective. This makes it a strong candidate for deployment in large-scale applications. Figure 4 illustrates the performance improvement of self-discover across 4 categories of reasoning tasks using PaLM 2L. The categories include multilingual, algorithmic, natural language understanding, NLU, and world knowledge. Self-discover shows significant improvement, particularly in tasks requiring world knowledge, with an average accuracy delta of 19.8% compared to direct answering and chain of thought, COT. This indicates that self-discover is particularly effective in tasks that demand diverse world knowledge, such as understanding sports, recommending movies, and identifying famous landmarks. Figure 5 compares the accuracy of different methods with the number of inference calls required per instance. Self-discover, which requires only one inference call per instance, demonstrates better performance compared to methods like COTI self-consistency, which requires 10 times more calls, and majority voting of each RM, which requires 40 times more calls. This highlights the efficiency and effectiveness of self-discover in large-scale deployments. Figure 6 presents examples of self-discovered structures on BigBench-Hard (BBH) tasks using the PaLM 2L model. The structures exhibit traits of atomic reasoning modules, including step-by-step thinking and reflect on task nature. Additionally, there is an example of creative thinking where the model devises an algorithm using a stack to solve a parenthesis parsing task. These examples highlight the adaptability and integration of multiple reasoning modules, providing insights into task-solving strategies. In this section, we delve into the self-discovered reasoning structures of self-discover. We highlight the importance of the 3 actions: select, adapt, and implement through an ablation study on GPT-4, showing consistent improvement in zero-shot reasoning capability with each action. We also demonstrate the universality of these structures by applying them across different models, such as from PaLM 2L to GPT-4 and from GPT-4 to Llama 2-70B, revealing commonalities with human reasoning patterns. Additionally, we compare self-discover with OPRO, showing that our method's self-discovered reasoning structures transfer more robustly and efficiently in a zero-shot manner. Figure 7 compares the reasoning processes generated by COT, plan and solve, and self-discover on a BBH geometric-shaped task. COT and plan and solve incorrectly assert that the path does not form a regular shape due to it not being a closed path, leading to a wrong answer. In contrast, self-discover breaks down each line segment, analyzes the coordinates carefully, and uses logical reasoning to conclude that the path forms a closed shape as it ends at the same coordinate, thus selecting the correct answer. Figure 8 presents the results of an ablation study on the 3 actions of self-discover: select, adapt, and implement, using GPT-4 on 4 reasoning tasks. The study reveals that each stage of these actions consistently enhances the model's zero-shot reasoning capability across tasks. Notably, the application of all three actions SAI results in task-specific adaptation of reasoning structures, providing the most significant improvement in solving reasoning tasks. In recent years, significant advancements have been made in the area of large language models, LLMs, prompting techniques. These include few-shot and instruction prompting methods such as those proposed by Brown et al. In 2020, Mishra et al. In 2022, and Wei et al. In 2021. Additionally, more advanced prompting techniques have been developed, including chain of thought, COT, prompting, least to most prompting, and decomposed prompting. Furthermore, search-based approaches like tree of thought, TOT, graph of thought, and branch-solve-merge have been introduced to enhance the reasoning capabilities of LLMs. The self-discover framework, adopted from Fernando et al., 2023, incorporates cognitive heuristics designed for problem-solving. It involves three key actions during stage 1 and 2 of the process. For evaluation, the authors used accuracy and exact matching, similar to other methods tested on BigBench-Hard and math. They manually examined outputs from large language models and designed heuristics to extract final answers. For the math dataset, they subsampled 200 test examples and manually annotated the extracted answers for all methods tested. Additionally, an error analysis was conducted on the math dataset to understand the failure modes of self-discover. This involved manually annotating whether the generated reasoning structures were correct and whether the model predictions using self-discover were accurate. A reasoning structure was considered correct if a human expert could solve the task by following it. Figure 10 illustrates the metaprompts designed for the three actions of self-discover during stage 1. Each metaprompt is structured with an initial and concluding instruction, detailed descriptions of reasoning modules, and task examples that do not include labels. Specifically for the implement action, a human-written reasoning structure in JSON format is provided as an example to guide the model. Table 2 presents 39 reasoning modules that encompass high-level cognitive heuristics for problem solving. These modules are adopted from Fernando et al., 2023, and cover a wide range of strategies, including critical thinking, creative thinking, systems thinking, risk analysis, and reflective thinking. Each module provides a specific approach to tackle problems, ensuring a comprehensive and diverse toolkit for effective problem solving. Thank you for watching.